Okay, let's go ahead and get started. So at the end of class yesterday, y'all voted and wanted a review day today. So that's what we're gonna do. So what that means is there's no new material covered today. There is a problem set that I posted that's just a whole bunch of practice problems reviewing all of the topics we've covered so far. So I made that one optional just because it's not new, it's just additional practice. So I will still, give you a completion check mark if you do it, but it's not worth any points. And I'll try to figure out a way to make it worth extra credit points. I will make it worth extra credit points. I'll just have to figure out how to do that. But if there's things you feel comfortable with, then don't do those practice problems if you don't want to. But it's just more resources for you to keep practicing. So the structure for today is I'm kind of gonna zoom through everything we did in the first 9 days in one day. So it's gonna be pretty fast. I'm not gonna go into a ton of detail. I'll go into a little more detail the second half because it seems like that's, it kind of builds on itself. So it seems like that's where people are most confused. So yeah, I'm just gonna kind of review everything we've talked about. We're not gonna do like practice problems in breakout rooms today. So just stop me if you have questions and want me to go in more detail on anything. And then while I'm on the topic of structure, next week, the first 3 days, we're gonna cover new material. And then on Thursday, I called on some friends who have GSI'd Chem 1A in the past. And so we're gonna have a panel for you guys to ask them questions and for them to give you tips and their observations of things that have tripped people up in the past. So that's going to be the last day. Okay, so reviewing what we've covered so far. So on the first day, we talked about matter. So chemistry is, I think today's homework is essentially a mock exam. So chemistry is the study of properties of matter and transformations of matter from one form to another. So matter is anything that has mass and takes up space. So just about everything you see around you, your chair, the air you're breathing, everything that you sort of can touch and that takes up space is matter. A substance is a pure form of matter. So if I have distilled water that is pure, just water, or like a pure diamond that has no impurities, but like my cell phone is made up of plastic and glass and metal and all sorts of stuff. So my cell phone is matter, but is not a pure substance. We also talked about phases. So solids retain their shape. Liquids have a well-defined surface and take the shape of part of their container. So they just fill sort of the bottom of whatever container they're in, and you can see where they end. And then gases fully fill their container no matter how big or small or whatever shape the container is. We also talked about properties of matter. So in particular, physical properties can be measured without changing the identity of the substance. So like mass, I can just put an object on a scale and I haven't changed that object or done anything to it, or color or size or any of those things that you can observe without having to do anything that changes your material. Chemical properties refer to the ability of a substance to be changed into another substance. And so those do involve changing your substance. So like reactivity, in order to see how reactive something is, you have to do that reaction and your material will change. So physical versus chemical, and then totally separately from physical versus chemical, there's also extensive versus intensive. So extensive properties depend on the amount of the substance and intensive do not. So mass is a great example of an extensive property. If I have more of something, it will weigh more. And so the mass depends on how much stuff I have. Intensive properties don't depend on the amount of stuff I have. So like melting temperature is intensive because water, no matter how much water I have, it's going to freeze at 0 degrees Celsius. So I think the main point of confusion here for people was that physical versus chemical is totally separate from extensive versus intensive. So you can have a property that's extensive and physical, extensive and chemical, and any sort of combination. So those are just two unrelated ways of characterizing properties of matter. On day 2, we talked about unit conversions. We also did a whole bunch of other stuff, but the most important thing was unit conversions. So if we have a conversion factor like 1 day being equal to 24 hours, the way that I think of this is that 24 hours divided by 1 day is 1, and 1 day divided by 24 hours is 1. So if we need to do a conversion, we can always multiply by that fraction, because by multiplying by 1, we're not changing the amount of, in this case, time that we're representing. We're just changing what units it will be represented in. And we always want our units to cancel out so that we end up with the units that we want. So in this case, we want to convert days into hours. So we need our days to cancel out. So we need days to be on the bottom. So we have 3 days times 24 hours per day. The days cancel out and we get 72 hours. So really don't memorize like when to multiply by 24 and when to divide by 24. You really just need your units to cancel out. And it's a really easy way to, screw up and lose a bunch of points if you have 24 on the bottom because you just like tried to memorize that you always divide by 24 or something. So another type of unit conversion is using prefixes. And so these prefixes help us deal with really big or really small numbers. And so you can look up a table like this. So for example, 1 megagram, which is a big M in front of the G that means grams, is 1,000,000 grams. 1 kilogram, which is a K in front of the gram symbol, is 1,000 grams, and so on. So I don't think you need to memorize any of these. That said, you will come across the ones in these red boxes a lot. And so I don't think I ever sat down and decided to memorize that a kilogram is 1,000 grams, but I just used it so often that I know it now. So for now, I think you just need to be comfortable using these if I give you the table or if you look up the unit conversions. But these are just a unit conversion like anything else. So just like 1 day equals 24 hours, 1 kilogram equals 1,000 grams, and you do your unit conversions exactly the same. The other important thing we talked about on day 2 was significant figures. And the point of significant figures is that we don't want to pretend that we're more sure than we are about a number. If I say that there's 2,000 people at this party, I'm not sure that there's exactly 2,000. I'm just saying like about 2,000, unless I have specifically counted, in which case I could say it's exactly 2,000. So when we're determining significant digits, all non-zero numbers are significant, and then zeros are the place where it maybe gets confusing. So if there's zeros between our non-zero digits, those are significant. So 101 has 3. Leading zeros are not significant. So like 0.234 has 3 significant digits. 0.0001 would have 1 significant digit. So if it's in front, that's just telling us the order of magnitude, and that's not significant. And then if I have extra zeros after the end of my number, those are significant. So like 0.400 has 3 significant digits. And then 2,000, just to give you more examples, 2,000 has 1, 2,000 with a decimal point has 4, and 2,000.0 has 5. So this is just how we determine the number of significant figures in a number. And then, I'm just kind of zipping through all of this, so please stop me if you have any questions. So when we're doing calculations with significant figures, when we're multiplying or dividing, we figure out the number of sig figs in each of our numbers and round to whichever one is smallest. So if I have 1,240 divided by 6, and I plug that into my calculator, what my calculator is going to spit out is 206.6666667. But 1,240 has 3 sig figs, while the number 6 only has 1. So I'm going to round to 1 sig fig. So the answer I'm going to box is going to be 200. So if the number is about 200, is about 2,000, what that means, if that's all I've written, is that it could be 2,200. We just know that when we round to the nearest 1,000, it rounds to 2,000. So if you want to signify that you're sure that it's 2,000 within a margin of error of 20, you would write 2,000 plus or minus 20. You would actually write out, here is the error that I'm sure of. So someone asked why 200 instead of 206. I have to round to one significant figure because the number 6 only has one significant figure. So I take those two numbers that are in my question and I find how many sig figs each of them have. So 1240 has 3 sig figs and 6 has 1 sig fig. So I have to round my answer to 200. If I rounded it to 206, my answer would have 3 sig figs. And I need it to only have 1. But when I'm adding or subtracting, I round to the least precise numerical place. So what that means is that if I'm doing 1240 minus 6, my calculator spits out 1,234. 1240 goes out to the tens place. So I know that it is, it could be, 1242, but it's not 1250. So 1240, I'm sure of, out to the tens place. And 6 goes out to the ones place. And so I go to the one that's least precise, so the tens place, and I'm going to round my answer to 1,230. So for multiplication and division, I'm just counting the total number of sig figs and rounding to the least number of sig figs. But for addition and subtraction, I'm looking at which place in my number has the last significant digit and rounding to the thing that's least precise. So the way the example that I always think about in my head is if I am at an event and I look around and I say there's about 2,000 people here, if 2 more people walk in the door, I can't suddenly say, oh, I thought there were 2,000 before, so there's exactly 2,002 now, because I was never sure that there were exactly 2,000 before. Does that help a little bit? So where this becomes important is when you're in the lab or you're doing experiments and, you're doing all these measurements and all these calculations. If there's some step where you weigh your material and you're only sure of it to 1 sig fig, I know this weighs about 10 grams, but it could be 11 or it could be 9 because you have a really bad scale or something, then whatever final answer you get, you really can't be that precise about it because some measurement that your answer depends on wasn't that precise. Okay. So on day 3, we moved into atomic structure. And yeah, it's the same rule with decimals when you're adding or subtracting. So if you have 1240.1 minus 6, then you would get, 1,234.1, but the 6 is still only to the ones place, so you have to round to 1,234. So the rule is exactly the same, it's just now after the decimal point. Okay, so on day 3, we moved into atomic structure. So atoms are made of electrons, protons, and neutrons. Electrons have a charge of -1 and protons have a charge of +1. Electrons weigh essentially nothing, and protons and neutrons weigh about the same as each other. Those protons and neutrons are in the nucleus. So the nucleus is positively charged. It's really small and densely packed at the center of our atom. And then we have this negatively charged electron cloud, which is where all the electrons live. So most of the mass is in the nucleus, and the electrons are floating around, and they're going to determine our interactions between our different atoms, because when different atoms come close to each other, they're not really going to see each other's nucleus because those are really small and protected by all these electrons, but they will see each other's electron clouds. So when we find an element on the periodic table, what these numbers mean is that 6 is our atomic number. So carbon has 6 protons. What defines carbon is that it has 6 protons. If you have an atom that has 7 protons or 5 protons, it's no longer carbon. So carbon will always have exactly 6 protons. The most common isotope of carbon will have a mass number of 12, which means it will have 6 neutrons. So if we average all of the isotopes, all of the atoms of carbon that we find in the world, on average, they'll have a mass of 12.011. So most of them will have a mass number of 12, which means they have 6 neutrons. And for a neutral atom, we'll always have the same number of protons and electrons so that their charge cancels out. So a neutral atom of carbon will have 6 electrons. But when we're talking about isotopes, like I said, an atom of carbon will always have 6 protons, but it can have a varying number of neutrons, which is why that mass number is not, that average mass is not a whole number. But if I tell you specifically, I have 13 carbon, that means that carbon will still always have 6 protons, and if it's neutral, it'll have 6 electrons. But in this isotope has 13 as a mass number. So this isotope has 7 neutrons. So that's the difference between like an atom of a specific isotope versus what you find on the periodic table, which is the average. So we talked about using the periodic table to figure all of this out, and you've been doing that all week. So I'm not going to spend too much time on this, but the periodic table is organized in order of atomic number, and you can find the mass of any element also on the periodic table. And in general, these are grouped with other atoms that behave similarly to them, which is what we take advantage of in valence electrons, which is what we're going to get to next. So on day 3, we just sort of thought about the electron cloud as just having all of the electrons, but in fact, those electrons are localized into shells or energy levels. And again, we're sort of making some approximations. So there's a whole lot of physics behind energy levels and orbitals. If you find that physics interesting, you can take a quantum mechanics class. I think quantum mechanics is really fun. It's really cool. But just for the sake of getting to the sort of physical behaviors that we see, we're sort of skipping all of that and just sort of, these energy levels exist, don't worry about it, which I know can be kind of frustrating. So there's definitely room to dive in that if it's something you're interested in. So when we're trying to figure out how the orbitals are filled, it's a pretty straightforward process. For a neutral atom, the number of total electrons is equal to the number of protons, which we can find on the periodic table. We start filling the orbitals from the lowest energy level first. So we start with 1 and then go to 2. And then in each sublevel, we have to give each orbital 1 electron before any orbital gets a second electron. So they like to share equally. And then valence electrons are those in the highest level that has any electrons. So hydrogen has 1 valence electron, it's in the 1s orbital. Helium has 2, lithium has 3, and now because we have an electron in our second level, now that second level is our valence electrons. So lithium has 1 valence electron and 2 core electrons. And then we just keep, as we move up the periodic table, we keep adding electrons to our orbitals. And then when we move up, now our third sublevel is our valence shell. And so when we have an atom with 1 valence electron and it becomes an ion, it wants to lose that electron, become positively charged. What it's going to do is it loses that electron. Now there's no electrons in the third level. So our second level is our valence shell now, and our valence shell is full. So you'll see that when we talk about ions in a minute. And so this is just the order that we fill these in. So this is one way to figure out how many valence electrons you have. And this gives us the most information about what orbitals are full, which orbitals have any electrons in them. But we can also use the periodic table. So the first column has 1 valence electrons. one valence electron, the second column has two, and so on and so forth. And if you remember, helium is a little weird because it has two valence electrons, but because its valence shell is the first level, which only has room for two, its valence shell is full. And so it is over there with the noble gases because it's happy its valence shell is full. It just only has two valence electrons instead of 8. And so you should be comfortable filling those orbitals, but also if all I ask you is how many valence electrons does sodium have, you should be able to just look at the periodic table and not need to fill in the whole orbitals if that's the only information you need. And then the other thing we talked about with valence electrons is Lewis structures, which are just a way of drawing how full our valence shell is. So if we have an atom with one valence electron, we generally draw it like this: 2, 3, 4, 5, 6, 7, 8. And so this lets us kind of see visually how many bonds it wants to form. So if somebody like oxygen has 6 valence electrons, then it wants 2 more, it wants to form 2 bonds. And so like we were just talking about, atoms want full valence shells. And so everybody in this last column are called our noble gases. Those are very stable. They don't want to form any bonds with anybody else because their valence shell is already full, they're happy. And so those noble gases are important, but they don't bond with anybody else. They're very happy to just float around as like one element, one atom of argon, not bonding with anybody else. And we can use that to our advantage sometimes. Questions so far on just atoms and electrons and atomic structure before we get to bonds? So day 5, we moved into chemical bonds. And so compounds are multiple different kinds of atoms bonded together. So this happens because these atoms want a full valence shell. So if carbon has 4 valence electrons, it wants 8. Hydrogen has 1 valence electron and it wants 2. So that's just because it's in that first energy level that only has room for 2. So for hydrogen, a full valence shell means 2 valence electrons. And so these guys make a deal with each other, and hydrogen says, I only have 1 electron to share, but I'm happy to share it with you if you share 1 with me. And so carbon finds 4 different hydrogens who are all willing to make that deal, and they form this molecule, which is CH4. And so you can always check whether a molecule is happy, because if you look at carbon, it has 8 dots around it, so it has a full valence shell, and each hydrogen atom also has 2 dots next to it, so they're all happy too. So this is why carbon always wants to form 4 bonds, and hydrogen can only ever form 1 bond because it only has 1 electron to share. Ions are anything that has a non-zero charge. So if I have sodium, it has 1 valence electron, which is in the 3rd energy level. And so it has 1 3s electron, and it has 1 valence electron. It would like a full valence shell, and so it can lose that 1 electron. Now the 2nd energy level is its valence shell, and it's full. So now sodium is happy, but it is a charge of +1 because it's lost 1 electron, and that electron is negatively charged. Chlorine, on the other hand, has 7 valence electrons, so it wants 1 more. So it gains an electron, becomes negatively charged, and now it has a full valence shell too. Ions want to exist in groups that are charge neutral overall. So 1 sodium atom will hang out with 1 chlorine atom. So the difference between covalent and ionic bonds is that in the case of a covalent bond, carbon and hydrogen both want more electrons than they have, so they share. They're covalent because their valence shells are overlapping while they share those electrons. So valent, valence, they're covalent, they're sharing their valence shells. In the case of an ionic bond, they don't both want more electrons. Sodium wants less electrons. Sodium wants to give up an electron, and chlorine wants more. So chlorine steals that extra electron from sodium. So that's the difference between covalent and ionic bonds. And then you don't need to memorize this word, but the thing that makes positive and negative charges want to hang out with each other is called electrostatics. So positive and negative things are attracted to each other. So those positive and negative sodium and chlorine atoms are still going to stay closely together because they like things of the opposite charge. And then the last thing we talked about on this day, which is the sort of constant point of confusion when you're first getting used to it, is line drawings. So just as an example, this was on one of your homeworks. I didn't feel like making a ton of lines in PowerPoint, so I just drew it on paper. So the first rule is that any element that's not carbon or hydrogen would be drawn like normal. So if I had an oxygen here, I would have a line going to a letter O. So if there's no letters, that means we only have carbon and hydrogen, because if we had anything else, it would be drawn like normal. So this molecule that I've drawn here is only made of carbon and hydrogen. There's no oxygen or nitrogen or anything else. The second rule is that wherever a bond is actually drawn, so you can see a line, but it's not specified what that bond ends in, then what it ends in is a carbon. So if I just fill in all of the carbons, everywhere a line ends, I've put a C. So this has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So just to repeat, wherever there is a line that's actually drawn, but you don't know what it ends in, it's a carbon, always. And then the last step is that, like we just talked about, carbon has 4 valence electrons. It always wants 4 bonds to make up 8 valence electrons. And it is not going to break that rule. So whenever it doesn't have 4 bonds, we need to add enough hydrogens to make sure that it does have 4 bonds. So if we do that, this first carbon only has 1 bond coming off of it. So it needs 3 hydrogens to make 4 total bonds. This guy has 1 bond coming off this way and a double bond coming off that way. That double bond counts as 2 bonds. And so it only needs 1 more hydrogen to make 4 total. So the same is true for most of the other ones, except this guy has 1, 2, 3, 4 bonds coming off of it. And so it's done. It doesn't need any hydrogens. So this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So what a double bond is I still only have 1 carbon on each side, but instead of each of them donating 1 electron so that they're sharing 2 electrons, it's each of them donates 2 electrons so that they're sharing 4 total electrons. So it's still just carbon, 1 carbon on each side, but they're just sharing additional electrons. And so that's why it counts as 2 bonds, is because this carbon is borrowing 2 electrons from this guy. So it counts as getting 2 electrons closer to its 8 valence electrons. So a single bond is 2 atoms sharing 2 electrons, 1 from each of them. And a double bond is them sharing 4 electrons, 2 from each of them. And a triple bond is them sharing 3 electrons each, so 6 total electrons. Why is it only carbon and hydrogen? So we've made these rules because molecules involving carbon and hydrogen are like the most common thing we come across. So they totally could have made the line drawing rules differently so that like carbon is always drawn, but oxygen is not drawn. That just wouldn't be very useful because it's carbon-based atoms that we are made of as people. And so when we're drawing molecules that are relevant for pharmaceuticals or like anything that's relevant to life, it's going to have a ton of carbons and hydrogens. And so because we draw carbon-based molecules so often, we picked carbon and hydrogen as the ones we were going to simplify to make our lives easier, so we have to draw less stuff. So that's where that rule came from, is just that organic molecules made of carbon and hydrogen are really common, and they tend to be pretty complicated. If you look at, the structure of dopamine or serotonin or any sort of biologically relevant molecule, they're big, and we really just don't want to write that many carbons. And so those are just like the rules that chemists devised a long time ago to make their lives easier, and we now just follow them. And so now that we have those rules, then we just know that if there was anything that wasn't carbon and hydrogen, it would be drawn like normal, and it's carbon and hydrogen that is simplified. Does that help a little bit? So if there was anything other than carbon or hydrogen, it would be drawn. And so because there's no letters drawn on this original line diagram, then it's only carbon and hydrogen. Okay. So I think this is a skill that I would definitely practice. If you do a Google image search for structure of serotonin, you're only gonna find it in line drawing form, because it's such a complicated molecule. So there were times for your homeworks that I was trying to find a full structure of molecules, and it was no one draws it that way. So it's really useful to have the skill of seeing a line drawing like this and knowing what it means. And as you get more and more practice with it, it'll get more and more automatic that you will look at a molecule and be able to sort of see where the carbons and hydrogens are going to be. So if it's not intuitive right now, that's totally fine, but it's something that you can definitely practice in. And it's also something that's pretty easy to get practice in, because if you Google image search line drawing, you'll find no shortage of various chemicals that you can practice on. And I'm happy to talk through more of these with anybody if there's ones from the homework that you want practice on. So you can just stay after class and we'll chat through it, or we can meet some other time. So then we moved into counting molecules. And so just as a reminder, here is our subatomic particles. And we defined the mass of a proton and a neutron to be about 1 atomic mass unit. And so when we want to count these, it's convenient to have a number, because 10 to the minus 27 is an annoying number to carry around. So if I convert 1 gram of protons to number of protons, I first have to convert this mass from kilograms to grams. And then I know that 1 proton weighs 1.67 times 10 to the minus 27 kilograms. All those units cancel out. So 1 gram of protons has 6.022 times 10 to the 23rd protons in it. And so we call that a mole. So that number is Avogadro's number. So you don't need to memorize these masses that are in here. I don't think I ever sat down and memorized Avogadro's number, but you're just going to use it a lot. So I wouldn't memorize it, but I would guess that by the end of Chem 1A, you will have it memorized by accident, just because you use it a lot. And so what that means is that 1 mole of protons weighs 1 gram. And because neutrons weigh about the same as protons, that means that 1 mole of neutrons weighs about 1 gram. Any questions? Okay. So when we're working with moles, we need our molar mass in order to make those unit conversions. So for example, if we find oxygen on the periodic table, that means it has 8 protons, and on average, 1 atom of oxygen will weigh 15.999 atomic mass units, or that 1 mole of oxygen atoms will weigh 15.999 grams. And so that's why that Avogadro's number was chosen using that unit conversion on the previous slide, so that these numbers are the same. So 1 oxygen atom weighs 15.999 atomic mass units, but 1 mole of oxygen atoms also weighs 15.999 grams. So if I have molecules involving hydrogen and oxygen, the molar mass of H2O is the molar mass of oxygen, which is 15.999, plus 2 times the molar mass of hydrogen. And the molar mass of oxygen is just 2 times the molar mass of oxygen atoms. And so this was an exercise we did in class that was a little bit confusing. So when we're asking which has more mass, a mole of H2O or a mole of O2, each molecule of, when we have a mole of each, we have the same number of molecules of each, because a mole is just a count of the number of molecules. So if I have the same number of molecules of O2 and H2O, O2 weighs more per molecule or per mole, and so we'll have more mass in that 1 mole of O2. But each H2O molecule has 3 atoms, and each O2 molecule only has 2. So there are more atoms in the H2O molecules. But because moles are just a count of total molecules, a mole of oxygen atoms has a mole of oxygen molecules has 6.022 times 10 to the 23rd O2 molecules, and a mole of water has 6.022 times 10 to the 23rd H2O molecules. And so those 2 piles of stuff will have the same amount of molecules. Does anyone have any questions on what a mole means? Okay. So when we're doing unit conversions, again, don't try to memorize when to multiply by the molar mass and when to divide by it. You should be able to just know that the molar mass is, like for H2O, 18.015 grams per 1 mole. So if I want to convert from moles to grams, I want my moles to cancel out, so I want the moles on the bottom. And so I'll end up with 72.1 grams. If I want to convert grams to moles, I want my grams on the bottom, so I just flip it. And I have 1 mole per 18.015 grams. So if I'm converting 52 grams to moles, those grams cancel out and I end up with 2.89 moles. And then there's a really important difference between moles and molecules. A mole is a count of the number of molecules, so they represent kind of the same idea, but a mole is 6.022 times 10 to the 23rd molecules. So if you want to count the molecules, you need to convert to moles. So you get those grams to cancel out. And then you need to convert to molecules using Avogadro's number. So 6.022 times 10 to the 23rd molecules per mole. Those moles cancel out and I get 1.7 times 10 to the 24th molecules. And so what this shows you is that in 52 grams of water, which is not a lot, we have 10 to the 24 molecules. So molecules don't weigh very much. Questions on unit conversions using moles?
So like when would you use moles instead of molecules? Or like when would you use molecules instead of moles?
Most of the time we're going to use moles because with any sort of practical thing that we are going to work with in lab, we're going to have multiple grams of stuff. And so it's going to be much easier for us to use moles instead of molecules. Sometimes when people are doing certain kinds of calculations, they need to count the number of molecules. For example, they know how much force there is between exactly 2 molecules. And so they need to get down to that level. But for the most part, it's going to be more practical on a lab scale. When we're working with 10 grams of stuff, it's going to be more practical for us to use molecules. So a mole is a count of a number of molecules. So 1 mole of molecules would be 6.022 times 10 to the 23rd. So there's a question in the chat about this unit conversion. 18.015 grams per mole is per 1 mole, in the same way that 24 hours per day means there's 24 hours in 1 day. So by writing it this way, I'm just leaving out that 1, but it's sort of implied. So there's 60 minutes in an hour. That's 60 minutes per 1 hour. Thank you guys for asking. Any other questions about moles? Okay. So day 7, we started talking about chemical reactions, which is when a type of molecule is converted into something else. So we call what we start out with our reactants, and our products what we end up with at the end. This is what we produce in our reaction. And as we write these reactions, our phases might be indicated using the SL, aqueous, and gas. So SL and G just means solid, liquid, and gas, and aqueous means the thing is dissolved in water. So this won't affect how we balance our reactions. It's just adding extra information to us so that we know the phases of the things that we're working with. So we write our reactions as going from reactants with an arrow to products. And so if we're making bread, we might say we have solid flour, solid yeast, and liquid water that goes to bread, which is solid. And if we need heat in our reaction, we indicate that with a little triangle on top of our line. And then the last thing is that the arrow indicates the direction that the reaction is going. So you'll often see it written like this. But if the reaction is reversible, which means it can go backwards from products to reactants, we can draw a 2-sided arrow. So when we are working with reactions, for example, this H2O2 goes to H2O and oxygen, we cannot create or destroy atoms. And so if we have 2 hydrogens and 2 oxygens on the left, and 2 hydrogens and 3 oxygens on the right, something is wrong. This isn't okay because we have created an oxygen atom out of thin air. So what we need to do is we can't just add an oxygen atom on our reactant side, because that would be changing what reaction is actually happening. But what we can do is change our stoichiometric coefficients. We can change how many of each type of molecule we have. So if we need more oxygens on the reactant side, the only thing we can change is how many molecules of H2O2 we have, because that's our only reactant. And so we can update our counts. We now have 4 hydrogens and 4 oxygens. And so now going back to the product side, we need to add some hydrogens and oxygens. And so because we need more hydrogens, we know we should play with our water. And so if we add another water molecule, now we have 4 hydrogens and 4 oxygens on each side, which means our reaction is balanced. And so the way that we would write that is 2 H2O2 goes to 2 H2O and 1 O2. So this is stoichiometry. So stoichiometry is just a fancy word for balancing our reactions like we just did. And those numbers that we've put in front of our molecules are called stoichiometric coefficients. So whenever you're working with a reaction, you always want to balance it first, or else you don't know anything about the ratio of how many of each thing you have. So when we're using stoichiometric coefficients, that's what that means. It tells us the ratio of the different molecules that we need. So if I have a reaction that's like 2A plus B goes to C, where A, B, and C are all some kind of molecule, then what that means is that I need 2 moles of A for every 1 molecule, 2 molecules of A for every 1 molecule of B to get 1 molecule of C. And then because moles are just counts of molecules, that means I need 2 moles of A and 1 mole of B anytime I want 1 mole of C. Questions about what stoichiometric coefficients mean? So on day 8, so 2 days ago, we talked about limiting reactants, which use those stoichiometric coefficients. So using that same reaction, 2A plus B goes to C. If I have 5 moles of A and 2 moles of B, I want to know which is my limiting reactant. And that means which reactant is going to run out first. And so for simple reactions like this, I can think about that visually, where I have 5 moles of A and 2 moles of B. Every time I make 1 mole of C, I use up 2 moles of A and 1 mole of B. And so I still have some of both left, none have run out. And so I can use up more. And now I'm totally out of B. So I can't make any more C. So no matter how much A I had, even if I had 5,000 moles of A, I still couldn't make any more C because I don't have any B. So our limiting reactant is the one that limits how much of our product we can make. And so as long as I only have 2 moles of B, no matter how much A I add, I can only make 2 moles of C. That's the best I can do. So if you have a simple case like this where you can just count, then you can probably figure it out intuitively like I just did. So A is left over. A is what we call the excess reactant. And just a wording thing, if they run out together, they're in what's called a stoichiometric ratio. So neither is limiting. Questions on that? Questions on what limiting reactant means? Okay. So this is the problem that you had on problem set 5, which I think tripped a lot of people up. So I think people understand conceptually what limiting reactants are, but it can be a little hard to use them. So in this case, the reaction I gave you was pentane being combusted. So a combustion reaction is always the thing that is being combusted plus oxygen goes to CO2 and H2O. And I've balanced that reaction for you right here. So you can always get more practice with balancing reactants, but just so we can focus on the limiting reactants, I just did that step for you. And then I asked you to calculate the molar masses of each reactant and product. People did pretty well on that. That's just using the periodic table and finding the mass of each of the elements that is relevant. So that was kind of the setup. And then the question is, I have 100 grams of C5H12 and 50 grams of O2. What is my limiting reactant? So some people just said O2 is my limiting reactant because I have less of it in grams. But that's not how we do this, because I need 8 moles of oxygen for every 1 mole of C5H12. Yes, so there's a question in the chat. When finding molar masses, you ignore the stoichiometric coefficients and you just worry about the actual atoms involved in 1 molecule of that compound. So for oxygen, I'm ignoring the 8. I'm just finding the molar mass of O2, which is about 32 grams per mole. So in order to know anything about how much C5H12 or O2 I need, I always need to convert to moles. And so the way that I like to find the limiting reactant, there are a bunch of ways that all work, but the way that I find is the most sort of consistent and will always work is I start with one of them and I assume it's the limiting reactant. So if I assume that C5H12 is the limiting reactant, I have 100 grams of it. The first thing I do is I convert to moles. I can't do anything using stoichiometric coefficients if I don't convert to moles. So I use that molar mass of 72.15 and I convert my 100 grams to moles. And then I figure out how much product I could make. In this case, I'm choosing to figure out how much CO2 I could make. I could have chosen to figure out how much total product I can make. It's going to get me the same answer because when I run out of my limiting reactant, I will have made the least CO2, the least H2O, and the least total product. So whatever way I pick, it's all going to work the same. So I just picked one product. I picked CO2. And I say, if I have 1.39 moles of C5H12, I can make 5 moles of CO2 per mole of C5H12. So that's using my 5 and my 1, my stoichiometric coefficients here. And so with that much C5H12, I can make 6.93 moles of CO2. And then with 6.93 moles of CO2, I can convert that to grams. And so I'm using the molar mass of CO2, and that means I could make 305 grams of CO2. Now I can check. So does anyone have any questions on what I did thus far? So if I now check, well, what if the O2 is the limiting reactant? I'm going to do exactly the same thing. So I'm converting my O2 into grams. So I have 50 grams of O2 and 1 mole of O2 for every 32 grams. So I have 1.56 moles of O2. Then I can use my stoichiometric coefficients. So in order to make 5 moles of CO2, I need 8 moles of O2. So I'm going to use 5 moles of CO2 for every 8 moles of O2. So that means I could make 0.977 moles of CO2. And then I convert those moles to grams, just like I did before using the molar mass. And so the most CO2 I could make using my O2 is 43 grams. And so if I'm running this reaction, at some point in time, I will have made 43 grams of CO2. At that point, I will be totally out of oxygen. And so I will never make 44 or 45 or 300 grams of CO2 because as soon as I make 43 grams, I'm out. So 43 is less than 305. So my oxygen is limiting. So some people did convert to moles and they were like, well, I have fewer moles of C5H12. So C5H12 is my limiting reactant. And that's wrong because yes, you have fewer moles of C5H12 than you have of O2, but you need 8 times as much oxygen in moles as you need of C5H12. There's a question in the chat. You absolutely can just compare the moles of CO2 to each other because the conversion factor is the same. So if I take 6.93 and multiply it by 44 and 0.97 and multiply it by 44, then this one is still going to be less in moles. So just to figure out the limiting reactant, it's okay to leave your answer in moles. I'm just going to need those grams in the next step, so I did it here. But you could just compare the moles to figure out the limiting reactant. The logic would be exactly the same. Questions on how I figured out my limiting reactant? So the most important takeaway here to me is that whenever you're comparing how much stuff you have in a reaction and how much you need, you always need to use your stoichiometric coefficients. That's what those coefficients mean. So for every mole of C5H12 I use up, I can make 5 moles of CO2 and 6 moles of H2O. Okay, so going on to the next part of the problem, I'm just going to copy what I found at the bottom here. So once I've made 43 grams of CO2, I'm out of O2. So O2 is limiting. What is the theoretical yield in grams? The theoretical yield is the most I could ever make with the amount of reactants I have. And so 43 grams is the most I could ever make because at that point I'm out of O2. And yeah, you should use sig figs for all of your calculations all the time. Sometimes I slip up and I forget. but feel free to call me out on it because I should be doing it all the time, and so should you. So my theoretical yield of CO2 is 43.0 grams. That's the most I could ever possibly make. I am telling you that in a lab, I ran this experiment and I actually made 30 grams. So my actual yield, how much I actually made in a lab, and this is something they would need to tell you, is 30 grams. My percent yield is how well I did versus the best I could have possibly done. So 30 divided by 43 is our actual divided by our theoretical. So what fraction of the max we could possibly have made did we successfully make? And we multiply that by 100 to make it a percentage. And so our percent yield is 69.8%. So if you had 100% yield, that would mean you made the most that you could possibly have made. You can't ever have more than 100% yield because that would mean you got atoms out of nowhere, of like you had, you ran out of your limiting reactant and then somehow got more. So your percent yield is always going to be less than 100. We're going to move into oxidation and reduction on the next slide. So if there are any questions about moles or yield or stoichiometry, feel free to ask them. Okay, so yesterday we moved into oxidation and reduction. There were a lot of words and definitions yesterday, but I am hoping that they make sense physically so you don't have to just memorize them. So oxidation increases the oxidation number. We'll talk on the next slide about how to calculate the oxidation number. But if something is oxidized, its oxidation number goes up. And oxidation means a loss of electrons. So if you like acronyms, I remember oxidation is loss, reduction is gain, which is oil rig. But you can also just think about it this way, which is reduction decreases the oxidation number or reduces the oxidation number. If something is reduced, it gains electrons. So reduction is gain and its oxidation number goes down. So electrons are negatively charged. And so the oxidation number goes down. So if you can just remember that reduction is reducing the charge or the oxidation number, then you'll be able to remember which one is reduction and which one is oxidation. So total electrons are always going to be conserved. So whenever somebody loses electrons, somebody else has to gain electrons. So if somebody is oxidized, somebody else is reduced. So if I'm oxidized, I lose an electron or some number of electrons. And in doing so, I have to give them to somebody else. Somebody else has to take them. So if I am oxidized, somebody else has to be reduced. And so by losing my electrons, I give them to somebody else, and that thing is reduced. So whatever is oxidized is reducing something else. And so if something is oxidized, it is a reducing agent. It causes something else to be reduced. And vice versa, if something is reduced, it oxidizes something else by taking its electrons away and is therefore called an oxidizing agent. So where this word came from is that oxygen is a really good oxidizing agent. So maybe this will be easier on the next slide when we talk about the rules for determining oxidation number, but you might remember that an atom of oxygen wants to be -2. So it wants, when it's in that elemental state where it's O2, it's at 0, and they want to be at -2. So they want to react with somebody to take their electrons away and oxidize them. So oxygen is a really good oxidizing agent because it wants to take electrons so that it can become -2. Does anyone have any questions on the definitions of oxidation and reduction and oxidizing agents and reducing agents? So for me, the only thing I memorize, which is still not really memorization, is that reduction is reducing the oxidation number. And from that, I can figure out that that means it's gaining electrons. Oxidation must then be losing electrons. And if I'm reduced, I must be oxidizing somebody else because I have to get those electrons from somewhere. So there are a few rules of assigning oxidation number. The first thing is that anything in its elemental form will have an oxidation number of 0. So if I just have like solid aluminum metal, that aluminum has an oxidation number of 0. And if I have O2, where I just have 2 atoms of oxygen, each of those will have an oxidation number of 0. And the way that I remember that is that by using the second rule, for any compound, the sum of the oxidation number of all of its atoms has to be its charge. So if I have O2 that has a charge of 0, then the total oxidation number of my 2 oxygen atoms has to be 0. So the total has to be 0, and it wouldn't make sense for one of them to be +1 and one of them to be -1. They're exactly the same as each other. And so those 2 oxygen atoms are going to be 0. So these 2 rules are always true. And then within that, we can use the other rules, which I like to just think about them on the periodic table. So there's a few exceptions for when these rules conflict with each other, but for the most part, if you just remember these rules, you'll get extremely far. So the first 2 groups want to be +1 and +2 for the same reason that those ions want to be a +1 and +2 charge. They have 1 valence electron or 2 valence electrons, and they want to lose them and become +2. The ones with 7 valence electrons want to get 1 more, so they're always going to want to be -1. The noble gases aren't going to react with anybody, so they're always going to be in their elemental form, and they're always going to be 0. And then oxygen wants to be -2. It really wants to gain those 2 more electrons so that it can be -2. And so what we do is, given these rules, if we have compounds, we figure out what the oxidation number of the things we don't have rules for is. So sorry, that was not very clear. So for CO2, for example, I have 1 carbon and 2 oxygens, and my total charge is 0. So I have a rule for my oxygen. My oxygen wants to be -2. And I have 2 of them. So for total, my oxygen is at -4. And so my carbon needs to be at +4 in order for my total charge to be 0. So whatever atoms you don't have any rules for, you use the atoms you do have rules for in order to figure out what their oxidation number needs to be. So this is one of those things that I think practice is just the best way of getting used to it. So there was practice on problem set 9, and there's more practice on problem set 10 as well. So if I have a reaction and I want to identify oxidizing and reducing agents, so column 3 is not necessarily +3. Usually if you have somebody in this column, it's going to be in a compound with one of the atoms that you do have a rule for, and you'll figure out its oxidation number based on that. Cool. So if I'm figuring out my oxidizing and reducing agents in a reaction, I'm giving you an example of magnesium plus chlorine goes to MgCl2. The first thing I need to do is figure out the oxidation numbers. On the reactant side, everything is in its elemental form. So magnesium doesn't have a charge right now, it's just in its solid form, and it's going to have an oxidation number of 0. Chlorine is also in its elemental form. There's no charge, it's just 2 chlorine atoms bonded together, and so it's going to be 0. And then on the product side, magnesium is going to be +2 and chlorine is going to be -1, which we can get using those columns on the periodic table. And so when we're figuring out our oxidizing and reducing agents, if you look at magnesium, it goes from 0 to +2. Oxidation is loss of electrons, so that means that magnesium is oxidized. It's losing electrons, which means it's giving those electrons to chlorine, and so it's reducing chlorine, so it's the reducing agent. So magnesium is oxidized, and it is oxidized by reducing chlorine. So on the other side, chlorine goes from 0 to -1. It gains electrons, its charge goes down, it's reduced. So chlorine is reduced, which means it's the oxidizing agent. It gains electrons by stealing them away from magnesium, thereby oxidizing magnesium. So I like to think through it logically because, as I've said a million times, I hate memorizing stuff, but you also can just remember that you flip it, like whichever one's oxidized is the reducing agent and whichever one's reduced is the oxidizing agent. But I like to understand where those things come from. And then the last thing we talked about yesterday is that when we had talked about stoichiometry, we only worried about balancing the atoms on each side. We still always need to do that because protons and neutrons can't be created or destroyed, but we also need to balance our electrons. And so if I have this reaction, I do have one copper and one silver on each side, so that's good. From like my day, whatever, 7 stoichiometry, this looks good. But if I look at the charge, there's a total of +1 charge on the left. I have 1 silver plus ion, and on the product side, I'm at +2. And so what that would mean is that this copper lost 2 electrons, but the silver only gained 1. And so what happened with that other electron? And so what we need to do is balance the reaction so that the charge is equal on each side, but we haven't screwed up the atom balance either. And so I need 2 silvers on this side to make the charge +2 on this side, but I still need 2 silvers on this side so that my protons and neutrons are still balanced. So now there's 1 copper and 2 silvers on each side, and the charge is balanced. So to give another example from your homework, if I have copper and lithium, so now copper is 3+ and lithium is 0, and then on the other side, lithium is +1. It starts out balanced with 1 copper and 1 lithium on each side, but the charge is not balanced. And so what I need to do is I need to make there be 3 lithiums on this side so that it's +3 over here and +3 over here, but I need to keep my actual lithium atoms balanced too. So I put a 3 in front of the lithium on the other side. So now I have 1 copper and 3 lithium on each side, which is good. And my charge is +3 on each side, which is also good. So I know there were some questions on this on the homework. Basically what we're doing is we're adding an extra step to our stoichiometry, which is to make sure the charge is balanced. For the most part, when you're doing stoichiometry, like those practices we did on day 7, nothing is charged. For a lot of reactions, there's no ions at all. And so you don't have to worry about balancing the charge. But if there's ions, you just also need to think about making sure the charge is balanced too. Any questions on this? Okay. So that is a review of everything we did so far. It was super quick, so I'd highly recommend if there's stuff you're confused on to go back to those problem sets and do those practice problems. Also, there's extra practice problems that I made last night. That's problem set 10, which include just like a few practice problems, new practice problems that weren't on the previous homeworks for each of the topics. And so if there's things that you feel like you need even more practice on after the homeworks, you can do that problem set as well. So that is it for today. I will, as always, stick around if anyone has any questions on anything. And then on Monday, so hopefully you can take some time to rest this weekend, and maybe if there's stuff you're behind on, get caught up. And then on Monday, we'll start moving into liquid chemistry.